thank you for the opportunity to present. Thank Don and the forum organisers for this, because I think we are at the point of having some new information about groundwater, based on relatively recent work by the Department of Water and by Rockwater consultants for Grange Resources. And it's an area that has mystified me for a long time, so I'm pleased that I think we've got a more coherent story. So the area that we're interested in is approximately shown on this map. This is the area of Sandplain, which is mapped by the geological map as sand, and is underlain by sedimentary rocks, which contrasts with northern areas, which are granite and hard rocks. But it's not an exact area, so don't read too much into that map. The underlying geology, I talked yesterday about that. In the north, the Yilgarn craton here, these are granitic rocks, 2.5 billion years old, very stable part of the Earth's crust. What's interesting about our area is this Albany Fraser origin, which is basically a range of mountains that was crushed up between the Yilgarn craton and Antarctica, which sat out here. And it has a predominantly east-west trend to the rocks in there, which we will see on a later slide. And then there are some younger rocks here, the Stirling Range, quartzites, Stirling Range and Mount Barron, which are sort of faulted outliers. These rocks here are granites and gneisses, so they're pretty similar actually to the Yilgarn craton. The Albany Fraser origin, the rocks are about 1.2 billion years old, or the metamorphism is something like 1.2 billion years old. So we're dealing with very old rocks here. The Stirling Range here, and Mount Barron about 1 billion years old. So here we see an aeromagnetic image. So this is measuring the magnetic properties of the rocks here. We can see here that the Yilgarn craton is fairly quiet, not a lot of contrast here, but the Albany Fraser origin, especially the Birren-up zone, has this predominantly east-west trend, which reflects in the more resistant ridges of more resistant rock, and intervening areas of less resistant rock. So we've got this east-west trend in the topography, which is now buried topography. So the next few slides I'm going to show are the evolution of the sedimentary rocks in this area. So this just shows from north to south, from the North Stirlings, the Stirling Range here, and what is now the Albany Sandplain, and we'll see the geology emerging. Here we have so this is Yilgarn craton here, the old rocks, the Stirling Range formation, and the Albany Fraser origin here. And the predominant rock types here. Whoops. Lost my point. Granite, the quartzite of the Stirling Range formations, and the gneiss and granite of the Albany Fraser. So back roughly around 60 million years ago, what was the landscape like? What we're inferring is that the drainage lines were running east-west, following the trend of the rocks in the Albany Fraser province, or Albany Fraser origin. Now, this is new information here showing these drainage lines in the Eocene, so about 45 million years ago. These were the drainage lines here. So these were have been explored by Rockwater for Grange Resources here, and many peaks. And down here, this information is from the Department of Water's drilling. So we have the King River Paleochannel here. What is now a paleochannel is an old riverbed, basically. and the Many Peaks area here. And yesterday we were just about here at the Sisters. And these drainages formed while Antarctica was just off the Southern Ocean here, just off the coastline, and opening up a seaway between the two continents. So 45 million years ago, this was the picture here, and subsequently Antarctica, of course, has drifted, or Australia has drifted northwards, so they've drifted apart. So basically about 45 million years ago, these drainages began to fill in with sediments. The first, the basal sediments here, the coarse sands and gravels right at the bottom of these valleys, fining upwards. So what we call the Werrellup Formation is these gravels, sands and gravels at the base of these old river valleys. They pass up into lignites and clay, so the amount of sedimentation is decreasing, and finer grain sediments are being deposited. Then the sea level rose and flooded these valleys with the deposition of the Palinuk Formation, which is siltstone and spongolite. So they're marine sediments covered the coastal plain here, and this is what we can see pretty much today in outcrop. Subsequent to the deposition of these Eocene sediments, possibly in the Oligocene about 30 million years ago, the land was tilted, so it was uplifted to the north and tilted down to the south. The effect of that was to alter the drainage pattern. So here we have now south draining drainage lines, which we see today. So this looks like the Calgan River is sort of in this position here, crossing these old river valleys. So we have a completely different drainage pattern. And the last geological event really is the deposition of the Sandplain. So this probably dates from the last million years or so, covering the Palinuk, surface of the Palinuk siltstone. So now we'll look at the geology in the cross-section. So this conceptual geology shows what we've seen on the previous slides. The Werrellup Formation here occurring in the base of these paleochannels, overlain by clays and lignites, passing up into the marine sediments of the Palinuk Formation, which have these irregular bodies of spongolite, which was talked about yesterday. Spongolite is a siliceous rock composed of sponge spicules and other fossils. It seems to occur irregularly within the Palinuk Formation. It's important for groundwater because it's vuggy, it's got holes in it, it's very porous. But the drillers have told us that it's randomly distributed. You can't predict its occurrence at any particular point. And here's the thin sand plain sitting over the surface. And one feature I haven't talked about is the sinkholes. There are reports of sinkholes in some of the depressions on the sand plain. So to look at the hydrology here, what we see is the rainfall decreasing inland, internal drainage at the base of the Stirling Range, forming these salt lakes here, maybe some movement of surface water, which Peter's talked about, across the sand plain with ephemeral wetlands, and in some places groundwater or surface water disappearing, draining down through sinkholes. And there's development of surface drainages along the coastal area. So looking at the hydrogeology then, here is the Werrellup aquifer, which is the main producing aquifer. It's got very coarse sands and gravels at the base, so you can put high-yielding bores in there. This is the Werrellup aquifer, is the town water supply for Albany, down at Sandpatch prison area. The same thing. We infer that there's a water table in the Pallinup siltstone, which is often in the region of 15 to 25 metres below the surface. And we are inferring that there's downward percolation through the Pallinup siltstone to recharge the aquifers in the Werrellup formation here. On the coastal area here, we can see seepage zones into the surface drainages with water coming out of the Pallinup. But as we talked about yesterday, the processes across the flat sandplain, and perhaps I've shown that a bit too horizontal, it should be sloping down to the sea. The processes here are mainly vertical, that the groundwater is percolating downwards without, although the water table slopes down towards the sea, because the Pallinup is fairly low permeability, the likelihood is that it can drain downwards much easier than flowing sideways. And in the sandplain here, we infer that we've got a perched aquifer that supports wetlands. There may be ephemeral wetlands. And spongylite here is shown again as an important source of water if you can intersect it in a borehole to get water out of the Pallinup formation. The salinity pattern then is dominated by the rainfall, the decreasing inland. So we've got fresh to brackish water, groundwater at the coastal areas, becoming brackish inland, and then as we come up to the base of the Stirling Range here, the Kojaneerup wetlands here, salt lakes, and in the groundwater that's in the Pallinup formation, in the Werrellup it's more saline, so the salinity generally increases with depth. So we've got fresh to brackish water on the coast here, saline in the middle, and hypersaline associated with these salt lakes here. This figure here, which was done by Adam Lillicrap of the Deep Earth in Albany, shows the salinity of boreholes, mostly in the Pallinup. So we can see the blue here is fresh groundwater. That's pretty well restricted to this coastal area here. Moderate salinity, so it's fresh to marginal water in that Many Peaks area that we visited yesterday, passing up into brackish water and then saline towards the base of the salt lakes in the Stirling Range. And the other side of the Stirling Range, to the north, the North Stirlings area, the groundwater is hypersaline, more than the salinity of seawater. So Peter has showed the interaction of surface water drainage to these wetlands here. How are these wetlands controlled by or affected by the hydrogeology? Wetland suites have been defined by the Seminyak Research Group. What they've called the Bailey Cup Suite are the salt lakes in the North Stirlings, the Kojaneerup Suite of salt lakes on the south side of the Stirling Range, the Pabelup Suite, which are wetlands with defined surface water drainage coming into them, the Many Peaks Suite, which we visited yesterday, are basically wetlands in closed depressions. Well, Peter's shown that they can overflow, but they don't necessarily have defined channels that you can see. And the Quallenup Suite are those wetlands which are ponded up against the coastal dunes. So so there's quite a variation, of course, in these wetlands, from freshwater wetlands, treed and vegetated, through to the barer surfaces of the North Stirling salt lakes in this slide. How do we think they interact with the groundwater? So we can look at several types of interaction here. The water table, if the water table is close to the surface, we could have through-flow lakes with groundwater sort of flowing through and the lakes reacting to changes in the groundwater level. The salt lakes are certainly inferred to have a groundwater table, shallow groundwater table here, in which there is evaporation and then also salty water, potentially draining vertically down into those into the Werrellup aquifer. A more common pattern, especially around the Many Peaks area, these ephemeral wetlands are well above the water table in the Pallinup siltstone. And probably there is these perennial wetlands are very likely to have some sort of low permeability layer well above the water table here. So these are perched and not connected with the regional groundwater system. And this seems to be the case with pretty much the wetlands that we know about on the in the Many Peaks suite. And in rare occurrences, we've told about sinkholes associated with these depressions here, and water can persist in these depressions and also drain downwards. So to conclude then, the separation of Antarctic from Australia created a hydrogeology, a South Coast hydrogeology, which is quite separate, quite distinct from the rest of the wheat belt north of the Stirling Range. That's probably something that's not widely understood. So there are up to 3 aquifers on the Sandplain, the superficial aquifer. The superficial sands certainly are a major influence on the wetlands. The semi-confined aquifer in the Pallinup, which is the main source of farm water supplies, and the spongylite within the Pallinup siltstone being quite important for bore yields. It's increasingly saline in inland areas, and the rise in water levels may well be threatening the freshwater lakes. And in the North Stirling's basin, the water table, which is saline groundwater, maintains perennial water throughout the year. And the confined aquifer in the Werrellup paleochannels is a source of drinking water for Albany. I should have changed that. Bremer Bay is actually from the Pallinup. But it does provide some opportunity for new industries, provided the water quality is sufficient. Water movement between the lakes, their catchments and aquifers is still poorly known, and we do need better knowledge if we're going to manage the wetlands in a more viable, more variable climate, which Bryson has talked about the drying trend. Thank you. Since we're well ahead of time, I might just mention one other factor. The Eocene sediments have previously been called the Bremer Basin, So that's this area here. This is a map of groundwater provinces, and the name Bremer Basin has given its name to the Bremer groundwater province. But recently, geologists, we've always recognised that the rocks here are the same age as those in the Eucla Basin here. Now, geologists tend to refer to this area as the Eucla Basin. From a groundwater point of view, though, the groundwater conditions that I've just outlined, which are the paleochannel sequence of sands overlain by silt, finer grained sediments, they are quite distinct from the hydrogeology of the Eucla Basin, which are karst limestone. So from a groundwater point of view, while geologists are calling this Eucla Basin, it's really quite separate, and I believe we should still refer to it as the Bremer groundwater province. Thank you.
Is there any questions from the floor to start? Because I've got one ready. Phil, when I was particularly working in the northern part of the Oyster Harbour catchment and even on our properties out at Bremer Bay, there's a lot of the dikes throughout the landscape and expression of surface water on one side of that or not. Can you just explain a little more about the dikes and how they will push groundwater to the surface and that sort of feature? Because it's quite prolific in some parts of the Sandplain.
I can't answer that question, no, because I'm not really sure about dikes in the Albany Fraser. I certainly seen dikes forming barriers in the Yilgarn Craton, but most of the and what I've been really talking about are the areas of sedimentary rocks. So the sandplain is broken up by these inliers of ridges, buried ridges of Albany Fraser rocks, which do come close to the surface, or in some places they are actually at the surface. Well, quite a few places. Obviously, we were standing on one yesterday on that granite area. So it's not something that I think that affects the sandplain to a great extent, because the sandplain is mostly developed over the Pallinup siltstone, which doesn't have dikes in it, because the dikes are a billion years old.
Great, thank you for that. Some questions for Phil. Thanks, Bruce.
Phil, with that Werrellup aquifer, how much does the salinity vary in the aquifer, either with depth or as you go north to south? Is it all the same salinity, or?
No, it's not. So we go back to the map. So yes, there's quite a variation. Obviously, it depends where they are in the geography of the place. So the main freshwater source is the King River paleochannel here that's been investigated by the Department of Water. So that's reasonably fresh from about here, certainly down into the bore field. In the Many Peaks area, I think it's fresh to brackish. This is information from Rockwater. And this one here you can see north of Wellstead goes back under the salt lakes, and this one has hypersaline water in it. So you're going really from hypersaline in the inland to fresh to brackish in this area and fresh here. So it does reflect the general trend of increasing salinity as you go inland. Does that answer your question?
Thank you so much for that amazing talk. Wish we'd known all this information 40 or 50 years ago before we cleared all that land with not much planning. I was wondering if you could detail a little bit more about the sands. You mentioned the sand dunes that came in and how we get the perch wetlands just tucked in on the north side of those. When did they blow in, and what climatic conditions caused them to blow in?
Yes, that's a good question because that's one I'd like the answer to. I certainly infer most of the sand is in southwest WA dates from up to 1 million years old. So the conditions it was deposited in are probably very arid times during glacial periods in the last 1 million years. What's the origin of the sands that we see on the sandplain? That's a question that we can't answer. In other areas of the state, the sand, like the deserts, the Great Sandy Desert, for instance, and the Little Sandy Desert, they are developed over sandstone rocks, so that sand has derived from the underlying rocks, and it hasn't actually moved very far. It's difficult to understand quite what the origin of the sand here is. It because it's covering the Pallinup silts, Pallinup Formation, which is very fine-grained, so it's not actually derived from the underlying rocks. It's obviously blown in from somewhere. So we can see some of the shapes of the lunettes around around some of the lakes. That the wind has obviously had great effect on building these dunes and the linear dunes as well. But no, I think the origin of the sand is a bit of a mystery at the moment. That needs to be explained. And we're not really sure about its thickness. I don't think the information is there about its thickness. That's obviously impinges on the ability to form an aquifer to maintain the wetlands. So that's another question that would be nice to understand. I don't know whether John Simon's talk that he's been doing more drilling around wetlands further east, so I don't know whether he could answer that question.